Assalamualaikum and hi everyone. So my name is Muhammad Fitri bin Sofyan. So I will present our project on quality evaluation and mechanical performance assessment of imported steel plates at ABC Engineering. So steel plates are widely used in construction, automotive and shipbuilding. Their performance depends on microstructure and mechanical properties, which can be affected by grain structure, heat treatment and material defects. Therefore, this project uses metallography, tensile testing and hardness testing to evaluate the quality of the imported steel plate. So the problem statement is ABC Engineering has received complaints regarding the performance of the imported steel plates, including reduced strength, poor ductility, and premature failure. This issue may be caused by material defect of improper heat treatment. Therefore, an investigation is needed to identify the root causes of these performance problems. Okay, so to address this issue, the objective of this project are to evaluate the microstructure, second, assess the mechanical properties through testing, and also identify the causes of failure and propose improvement to enhance the performance and reliability of the steel plates. And last but not least, to develop teamwork and problem-solving skills.
Hello, my name is Tunesh Kumar, and I'll be explaining about the research planning and experimental design. So, for the first one, we have the hardness test. Hardness test is used to determine the hardness of the material while using the Vickers method with 1 kgf load. Then, it is also helps to detect the non-uniform hardness of the specific material. Then, for add-on, it helps also to identify the possible decarburization and which relates to the hardness of the microstructure. Then moving on, we have the tensile test. Basically, tensile test is used to measure the yield strength and also the ultimate tensile strength. On top of that, we also use tensile test to measure the percentage of elongation of the specific material. Since we're using percentage of elongation, we also get to evaluate the ductility of the specific material. Then, while using tensile test, also we get to observe the necking behavior of the specific material, and also we get to study the fracture mode. Then moving on, we have the metallography. So how is metallography being prepared is by polishing the specimen and also by apply etching using nitrile solution around it. While doing this, we get to observe the grain structure. Then this process also helps us to identify the ferrite and pearlite phases of the microstructure. Then metallography also helps us to detect the defects such as cracks or inclusion in the material. And last but not least, it helps us to analyze the heat treatment effect. Next, moving on to safety and laboratory procedure. First thing first, we have personal protective equipment, also known as PPE. It is important for us to wear lab coat for protections, use safety goggles to protect the eyes, wear gloves when handling specimens, use closed-toe shoes to protect our foot for protections, and last but not least is to wear face masks when exposed to dust or fumes. Then for the tensile test safety, it's important for us to ensure proper specimen alignment. We have to keep safe distance during the testing of the tensile test. Then keep hands away from moving the grips. Set correct lead and extension rate. Last but not least, we have to follow the standard machine operation procedure which is given. Then moving on to the hardness test safety. It's almost similar to the tensile test safety. First thing first, we have to position it in a specimen accurately. Then we have to avoid contact with indenters, handle sharp specimen carefully, and remove specimen only after indenters is retracted. And lastly, we have to use the correct test load. Next, the safety of the metallography. It is divided into cutting, grinding, and polishing and etching. So for the cutting, we have to secure specimen firmly, and we have to keep our hands away from rotating blade. Then grinding and polishing, we have to hold the specimen firmly. Then we have to avoid loose clothes because it might enter inside our body. Then we have to wear face masks all the time to avoid dust and protection, same as PPE. Then lastly, we have etching. Etching, we have to use gloves when handling chemicals. We have to work in fume hood. Lastly, we have to follow proper chemical disposal procedure to get rid of the chemicals. Thank you.
Next, we go to the experimental procedures. So for the tensile test, we first measure the initial dimensions using the vernier caliper. Second, we mount the specimen in UTM and attach the extensometer and apply the tensile load until fracture. Then record the load and elongations so that we can generate a stress strain curve. Then finally, we measure the final gauge length and analyze the results. And for the hardness test, we clean and polish the specimen surface, select a Vickers indenter and load, and apply load and create indentation so that we can record hardness value, then repeat the test about 3 times for accuracy, and then lastly we calculate the average and the standard deviation. The metallography test. First we cut the specimen to thickness of approximately 10 mm, and then we mounted it in resin for stability. Then we begin the grinding phase by using a 240 grit silicon carbide paper and progressively move through thinner grits from 300, 220, 800, 1200, and finally 2000s to achieve a uniform flat surface. Then to achieve a reflective mirror finish, we use alumina or silica polishing suspensions. Once polished, we applied the nickel about 2 to 3% concentration. This etching step is critical as it reacts with the surface to reveal the underlying grain boundaries and faces. Then finally, we place the sample under the microscope. We observed the structure at magnifications ranging from 5 times to 50 times and captured micrograph, which we will now use for our detailed structural analysis.
Slide show the microstructure of the steel samples. We can see that ferrite and pearlite phase are present, but they are not evenly distributed. The grains are relatively coarse, which means there are fewer grains boundary to stop the dislocation movement, resulting in lower strength. In addition, non-metallic inclusions and defects are observed, which act as stress concentration points. These defects can initiate microcracks, leading to early failure of the material during service. For the mechanical properties, the tensile test shows a yield strength of 250 MPa and ultimate strength of 400 MPa, which are slightly below expected values. This is mainly due to the core grain structure and weak internal bonding. The elongation is about 15%, indicating moderate ductility. The fracture behavior shows a mix of ductile and brittle characteristics, meaning the material does not deform uniformly. The hardness range from 120 to 150 HB, showing variation in microstructure where pearlite-rich areas are harder and ferrite-rich areas are soft. This slide connects our lab findings with the client's complaint. The reduced load bearing capacity and premature failure can be explained by the lower strength and non-uniform microstructure. The variation in hardness leads to inconsistent performance across the steel plates. Furthermore, coarse grains and inclusions create stress concentration points, which initiate cracks and reduce structural reliability. Overall, the material properties directly contribute to the issues reported by the client.
Moving on, here are the key findings from our investigation. Simply put, the material is underperforming because it's not strong enough. Our lab test showed a yield strength of only 250 MPa and an ultimate strength of 400 MPa, which are below what we need. The root cause is a bad internal structure. Under the microscope, we saw coarse grains. This means the grains are too big. Large grains have fewer boundaries to stop the material from deforming, making it weak. We also found inclusions or tiny defects that act like a magnet for stress, causing the steel to crack and fail early. This whole mess comes down to improper heat treatment and inconsistent cooling during manufacturing. To fix these issues, we need to overhaul how displays are made. First, we recommend a quenching and tempering process. This specific heat treatment will directly increase the steel strength and toughness. Second, we need to use controlled cooling to achieve grain refinement. By shrinking the size of the grains, we create more boundaries that make the metal much harder to deform. We also need better temperature control to make sure the structure is uniform across the entire plate, so we don't end up with soft spots. Finally, ABC Engineering must implement strict quality control. This means performing regular mechanical tests and microstructure inspections on every batch to catch defects before they ever reach the client.
In conclusion, the import steel plates showed quality inconsistency due to microstructural defects, low mechanical performance, and improper manufacturing control. This issue affected the strength, reliability, and overall performance of the material. Therefore, the improvement in heat treatment, manufacturing consistency, and quality control are necessary to ensure the steel plates meet required engineering standard. That's all from us. Thank you.